Okay, so what I'm going to talk to you about here is requirements for a mission to study Thermosphere-Magnetosphere Coupling. There's a cast of characters here. We wrote a white paper for the decadal survey recently. Of course, we had a bunch of opinions about what those requirements would be. Just to review a little bit of not so recent history. The declined finalists in the most recent Explorer competition included missions which, taken together, would have been a really beautiful constellation for MI coupling studies. ASTRI was a 3-axis ram-pointed atmospheric probe with a dipper capability to come low down. Targeted ion-neutral interactions, and OMIC was a twin image. Jim Birch talked about it earlier this week. Was a twin imaging in situ spinner mission targeting the auroral acceleration region. Put them together, beautiful. They were declined. Reminds me of this quote from Ben Franklin: "We must indeed all hang together, or most assuredly we shall hang separately." So I'm doing some soul searching about what this means, and I think it points toward the need to have a true MI coupling package that is focused enough to be done in an affordable Explorer opportunity, which is going to be coming up at some point. In the decadal, thanks to efforts of people like Bill Lotko and others, there appeared this as an imperative for the solar wind magnetosphere interactions group. And there actually was a kind of a similar one in the Atmospheric-Ionosphere Mesosphere, to initiate a strategic mission like MISTI to simultaneously measure inflow of energy to the upper atmosphere in response to the ionosphere-thermosphere system to this input. MISTI standing for MI source term energetics goals that fit in with NASA's strategic plan and the decadal charter, kind of as shown there. So there is sort of a decadal level community buy-in to doing this kind of mission. Of course, the part that I put in the ellipsis up there, ... said, resources permitting. Okay, so that's the challenge. But why did the whole community buy into such a narrow topic as ionospheric outflows? And it's because, of course, they have tremendous impact on what we think should happen in the magnetosphere, given observations, given new multi-fluid simulations. This is a thing from Katie Garcia-Sage et al., and it basically shows, somewhat analogously, but in a more or less specific sense than the Bramble study, shows that when you have outflows, as in the bottom, and when you don't have outflows, as in the top, in our best knowledge of the magnetosphere, you find that the magnetotail is just much more dynamic, more stretched and more dynamic with the outflows than it is without them. I mean, and there's the crux. Outflows enhance the magnetotail storage and release cycle. They look like that mass and momentum of ionospheric outflows is actually what's tearing loose the tail, somewhat analogously, but for different reasons than the Jovian satellite outflows are tearing loose the tail there. So this is my attempt to rack up a little bit of what you might call myths, facts, and mysteries about outflows. I think it's a kind of a established myth in our field that they take 10 electron volts per oxygen ion to achieve, which isn't a very large energy by magnetospheric standards, but I'll argue to you that really more like a 1 or 2 electron volts is all that's actually needed to get an oxygen ion out because of the AmBipolar potential that exists routinely and permanently, basically, because of photoelectrons and other superthermal electron populations. It pretty much, I mean, you might almost think you ought to have wholesale outflow of oxygen all the time, but we know that's not true. No outflow results from Joule heating. We often hear this. I think actually energy that's put in below the sonic point, in other words, Joule heating, is very much instrumental in increasing the flux of the outflow, whereas energy put in above the sonic point like auroral acceleration, is mostly instrumental in boosting the velocity of the flows, which of course affects where they go in the magnetosphere. But if we're focused on the flux and how to get material out of the ionosphere, I think we've got to focus on the lowest energy inputs to the system at the lowest energies. Another kind of myth, I think, is that current-driven wave heating ought to be the dominant source of heat. That is, parallel current-driven wave heating. And in fact, when Bob Strangeway really went looking at that, he found that the lowest frequency, essentially DC ELF waves dominate that, and they're not really current-driven waves. It's convection and the things that happen to convection. So I think the real mysteries, I argue to you, the real mysteries are how does electron-driven ambipolar field drive and respond to ion outflow and heating? How does it get set up and how is it distributed? How's the energy transported to the exabase region down where the ions and the neutrals are together and new ions are being formed and they're charge exchanging and et cetera? How does that enhance the escape flux? And where and why do outflow effective waves grow? There are definitely outflow effective waves. Where do they grow? How do they propagate? And where do they dissipate? And I would bottom line this by saying, how do thermospheric density, electron precipitation, and broadband Poynting flux combine to determine the outflow flux, velocity, other characteristics? So, a little bit about the AmBipolar potential. Paper that I participated in with George Kazanoff showed that if you form an aggregate potential as the sum of the gravity, ambipolar, and ponderomotive potentials, and just consider the cases for practically zip ponderomotive here for a second, the effect of combining gravity and ambipolar potential is to pretty much null out the gravitational potential, except down near the bottom where you retain a binding potential that's quite small, just a volt or two. You can see here, this is kind of a magnified version of what you're seeing over here. And these two plots are basically the same, except that one is with convection electric field as a ponderomotive influence, and one is wave electric field as a ponderomotive influence. You don't hear that much about ponderomotive effect, except from certain Swedes and George Kazanoff. But I think it's probably important and needs to be considered in the mix. But even just the ambipolar potential is reducing the gravitational binding by quite a lot. Now, we learned a heck of a lot about ionospheric upflows, maybe outflows from ASCAT radar discoveries, which resulted in defining two types of upflows, type 1, type 2. One was because of ion heating occurring mid-altitude range, a few hundred kilometers in the radar field of view, and upflows that resulted from that. The other type seemed to be relatively distinct, although sometimes they could be combined into aggregate or additive effect. Electron heating was equally effective in producing the outflows. Here you're seeing the red is upward flow at the top of the radar range, just below 900 kilometers. Looks pretty similar here and here, but one case is electron heating, one case is ion heating. So electrons heating, ion heating, they're both equally powerful in terms of moving plasma upward. Oh, and the thing I don't want to forget here is the non-thermal ion velocity distributions that were also observed by radar in the same time frame. And they were widely interpreted. Just, these are the backscatter spectra from regions of the ionosphere that were being heated, were widely interpreted, maybe not uniquely, but at least interpreted as evidence for distribution function type that I think as plasma physicists we have to be interested in. This is a simulation from Gordon Wilson et al., where he's looking at velocity space for altitudes of 3, 4, 5, 6, 700, 900 kilometers, and time evolving within his simulation. And you can see transverse broadening of, this is perpendicular velocity and parallel velocity. You can see perpendicular heating starting to appear here, and then that is not perpendicular heating. That is perpendicular acceleration. That's pickup ions going on in the ionosphere at a few hundred kilometers. You're getting two distinct peaks with ions going around in circles, gyrating, just like the ions in the cometary ionosphere or satellite pickup within a magnetosphere. And you can see that in this simulation, which didn't have wave heating of any kind in it, it was just collisions between ions and neutrals, you formed quite a deep minimum in the center with a donut or toroid-shaped, ring-shaped pickup ion distribution, and it evolved upward in altitude and looked kind of like an ion conic up here. I think you'll have to agree that looks like an ion conic. Of course, things are still evolving at the end of this simulation, but I just have been fascinated with this ever since I read that this should happen in papers by Jean-Pierre Saint-Maurice and others. Back, I think I didn't read them until the middle 80s or so, but so if you look at what's the distribution in V-perp here, this little box, here's a couple of examples, just comparing with what is seen in the auroral upflow, ion upflow. This is from Freya, from Mats Andre, and you see that the energy distribution, we're kind of fixated on the angular distribution in conics. But the energy distribution is very interesting as well. It's a power law. It's not a bi-Maxwellian, it's a power law. And it's extending up to tens of kilometers per second. And very interestingly, I think, Patterson et al. Reported that when the space shuttle releases neutral gas, for various reasons in the vicinity of the space shuttle, you form a new ion population. These are the thermal ionospheric background ions. You form this new population. Son of a gun, it has a power law distribution. And actually, this is just the energy distribution. They were able to resolve the fact that they were pickup ions as well. So you're basically forming new ions from the neutral gas that the shuttle was releasing within as it's flying at 8 kilometers per second through the ionosphere. And you basically pick those new ions down to the ionospheric frame of reference from the shuttle frame of reference and gave them an amount of energy that was comparable. The trick is, or the funny thing here is, that you get a power law energy distribution from what starts out as just a pickup distribution. So there's some kind of energy diffusion going on. Okay, so let me try and summarize using a bit of an elaboration on Bob Strangeway's figure here. And I'm going to sort of appeal to the same triumvirate of regions that Carol Patty referred to earlier, the collision-dominated lower region, the magnetized upper region, and a transition zone around where the exobase is, where you're basically going from collision-dominated to magnetized, and you have the anisotropic conductivity. But I think this is the thing that's not widely realized. When you have that anisotropic conductivity, if the flow velocity between the ions and the neutrals is larger than the thermal speed, you have essentially pickup ions going on, being created there, a hole in velocity space being created, and gradients of phase space density that are going to generate waves. So you have a local wave source potentially right in the middle of your problem here. So no question there are waves coming down from outside, from up higher altitudes. And there's kinetic energy coming down in the form of precipitation from higher altitudes. And it's all incident on the dense atmosphere, but operating through a region where ions and neutrals are having relationships of which we need to be tolerant. And maybe we even need some affirmative action to go into that region and study it a little bit more carefully. But I claim there's ion pickup and wave particle interaction pressure or ponderomotive effects, AmBipolar potential effects, and in the wave dissipation of waves coming from outside the system, creating an anisotropic distribution function that can be, of course, Bob has shown us earlier how ambitious one can get in treating all of these different effects in 3 dimensions and 4 dimensions, including time. But you can also think of it, at least from a heuristic point of view, as a generalized kinetic escape, like Jean's escape. You just ask what part of the distribution function is free to escape and which parts are going to hang around. And you can at least get a qualitative idea of what effects are doing what from that. But we need to measure a lot of this much better than we have. We haven't, just the idea of resolving with a plasma analyzer those non-thermal distributions, it hasn't been done. And it's difficult to do because they're just down in the EV energy range. Okay, so what's one proposed approach to this? And I throw this open for discussion soon here. But one thing I can envision, or we can envision doing, is having an F-region boundary, lower boundary, if you will, sensor and imager system that consists of incoherent scatter radar, Canadian all-sky imaging chain, imaging at least the North American continent, and with meridian scanning photometers and all-sky imaging, you can get a pretty good context for what's going on there. But then you need to need to have probes at the magnetospheric boundary so you know what's coming in before it gets affected by the presence of the neutral atmosphere. And then you need another one that's right in the middle of the neither magnetized nor collisionally dominated region, the transition zone, where you can look at the effects of the upper and the lower boundary being impressed upon that transition region. So one way of deploying this, I think, might be with mission orbits that look like this, where they have opposite but equal apogees. So one is low and one is high as you go over the auroral zone on one side, and they reverse rolls over on the other side. And of course, this processes around the Earth and gives us a normal sort of statistical picture of what's going on. But you also have kind of leading and following passages over the other two auroral zones per orbit. Nothing too challenging about doing this. These are orbits you can easily imagine getting to and station keeping so that they are maintained. So that's one idea, at least for. Now let's talk a little bit about the payload that you might put on the upper two spacecraft, which would presumably be identical. I think you need to worry about the gas. We've learned from CHAMP that there are big, substantial puffings up of the thermosphere in the auroral zones, especially in the cusp, but in the auroral zones. 2 minutes. Mm-hmm. To the 20 minutes. Yeah, okay, I'm good. Here's a result comparing CHAMP, or correlating CHAMP upwellings, if you will, with ion outflow. And I kind of take issue with the way the plot's made here. They got the abscissa on the ordinate and vice versa. But here's the flux increasing from left to right with increasing deceleration, or that is, increasing density of the neutral gas. So it looks like the outflow is more productive when it occurs within a region of higher gas density. Can't we do better than accelerometry for measuring the neutral atmosphere? I think we would like to have density composition and gradients from the two spacecraft. The upper one, depending on how high it is, it may be challenging to measure the neutral gas there, but that's the objective, I think. For fields, of course, we need the sort of standard stuff, radial and axial electric fields, flux gate magnetometer, search coil magnetometer. We want to get the waves, the polarization, and I really think we need to get their interferometry so that we know the K vectors, which way the waves are going, what the gradients are and the intensity of the waves from the upper to the lower spacecraft, say, and which way the waves are going. So we know where the dissipation is and where the source is of the waves for different modes. And then we need the intensity gradient. Well, I just mentioned that. But you'll notice over here, this is a Themis-like spacecraft bus, which happens to fit in a Pegasus. So that's sort of part of the picture. And here's, for the plasmas, we need to do this core plasma. We need to actually measure the hole in the middle of the distribution function and the pickup ion effect occurring within the plasma down at the EV level. So this is 1/10 of an EV to 100 EV focused instrument out on a boom. It needs to be out where it can control its effective spacecraft, its effective potential relative to the plasma. It needs to have a 360-degree field of view in a cartwheel mode so that it can see the ram direction all the time and measure when we're just going through cold gas. We'll be able to diagnose that. when we're going through a hot or a pickup ion distribution, we'll be able to recognize and observe that. There'd be deflection back and forth across the RAM in the polar angle, axial polar angle. So we need to be able to do gradients of all that at the 2 different spacecraft, and then of course we need the hot plasma as well. Electrostatic analyzers would be absolutely essential. Really would like to have composition for that as well. So precipitating ions and electrons. And this is sort of a quad chart. So this is a wrap up right here. Just summarizing everything I've been saying about one possible mission for this purpose. So thanks. Appreciate your comments.
Thank you, Tom. Are there any questions? Yes.
Do you need onboard propulsion to fight atmospheric drag? And if so, how big of a cost driver?
You'd need it to deorbit these at the end of the mission. You'd like to have it, I think you need a lot less onboard propulsion than Themis needed. Okay, we're not going to go to the moon with these, right? So my thought is that you could essentially provide for a Themis-like propulsion capability, but with far less fuel available. And you could that would help to maintain the relative positions in the most advantageous arrangement.
Yeah, and I'm sorry, this is a science question, not a mission question or science comment. But as far as the, you can't tell where it's coming from, can you? You know, as far as this drift between ions and neutrals in the strong field region, of course, this is well known in the ionospheric community to give you things like Farley-Buneman instabilities, which limit how much relative velocity they have. I don't know if George Kazanoff had that in his simulations, but those sorts of instabilities are also potential sources for heating and upwelling and stuff like that.
Yeah, there's a host of instabilities that and some of which have been worried about, but I think far too little actual plasma physics has been done in particular on the pickup ion distribution with the hole in the center.
My comment, Tom, and we're getting to be probably far too ambitious, but besides getting neutral density and composition.
Wins. Yeah, I think if this were to graduate to a mid-X, right, from what we think is more likely in the next round of a small explorer, then you might easily consider elaborations like that.
My follow-up to my
Sure.
point, though, is that these sorts of instabilities will tend to smear out that ring distribution.
Well, I mean,
think.
the ring distribution is itself a source of the plasma waves that will destroy it and thermalize it, right? Probably maybe there are other instabilities as well, but it is itself,
first, yeah.
right? In fact, it is itself the biggest DFDV that you could ever imagine in a plasma because those densities are high and the velocities are tiny. So DFDV is huge.
Tom, if over here, if you're only coming down to 500 kilometers, that's where you're
with the
talking about your
spacecraft,
deepest.
right? But
With
don't
the
forget
spacecraft.
the radar. The ionospheric boundary conditions being provided by radar and imaging.
So, but you also really want to know the composition within that sort of that in-between range where you're only going to be looking at it, looking at the source population without composition, yeah?
I don't think I'm following you.
So if you're looking at the ion outflow source, I suppose you're looking at it at your 500 kilometer upper boundary range, right?
We're looking at it at a couple thousand kilometers, 1,500, 1,500, 2,000, 500, and then you're getting some kind of measurements at 200 to 500 kilometers from the radar, and particularly from incoherent scatter radar.
Okay.
And all of those are composition.
Just a quick footnote from what I said. You can get some wind information from ground-based observation. If John Merriweather would be here, he would be jumping up and down.
Well, and I'm trying to respect the fact here that the real source of our knowledge about type 1, type 2 outflows is incoherent scatter radar. running from a couple hundred kilometers to 800 or so. Oh, neutral gas. Yeah, no, that's another good point. It'd be nice to have a third neutral gas measurement, right? Neutral wind. Yeah, oh, right, Merriweather's. Good point. I hear you. Now I'm finally getting it.
So I like this mission concept quite a lot, but I wanted to ask about the upper range of the altitude. So the highest measurements will be at 2,000 kilometers. And I was wondering why you chose 2,000 kilometers, and what are the restrictions on
Sufficiently high to be a few scale heights above 500 kilometers. That's the main requirement, so that you're totally in the magnetized region and not in a region that's much influenced by the neutral gas. So it's a magnetospheric boundary condition. Then you have an ionospheric boundary condition from the radar, and then you're looking at the conflict between what the magnetized plasma up high is trying to do and what the gas is trying to do.
I was just wondering because, I think it's unknown right now, really, what the altitude extent of the wave heating region is.
Right, well, I don't think you need to cover the entire wave heating region. And one of the points I made was wave heating that goes in below the supersonic outflow level affects the flux. And if it goes in above that level, it has little or no effect on the flux, but just affects the velocity. We've been studying the upper effects for quite a bit. I mean, we could have 5 spacecraft and do the whole thing at once, but I'm trying to keep this focused to the region that's least known at this point, least sampled.
Yeah, to follow up on that, it's been known that, first of all, the point that once you've got the flux escaping, flux is flux, you can't change that. You're not making new material.
That's what I mean by the sonic point being
right, absolutely. But the other point is, there have been observations that wave heating continuing on the way up, but you've already established what the outflow is by that stage.
You're just making it go faster if you heat it above that point.
But the other point is if you go too high, especially on the night side, you start to hit the auroral acceleration region, and then you're, in essence, you're beginning to mix up your inputs because the acceleration region is itself a point of dissipation, whereas once you're below it, everything that's coming down has basically set itself.
It's picking the right boundary level as a boundary condition for what's going on in the exobase region. The exobase region, I think, is really arguably controlling the flux.
Right.
And that's the focus.